Hey everybody, this is Vectors Part 2, day number 3. Alright, two ways to determine the equation of a plane from two vectors and a point, as well as finding the normal vector first. The normal vector is just going to be a vector that's perpendicular to the plane that we're dealing with. Okay, so let's get started and do a little bit of review to start with. Okay, this problem is a review of yesterday's material. So I'm not going to record the entirety of this problem just to keep the length of this video to a minimum. But I will post the answer here so you can see it here in just a second. Okay, so condensed version you got here. Here's our vector equation of the plane. We would put it into parametric, eliminate lambda and mu, and then you should get this equation for your plane. Okay, let's move on to new material. And actually, while I'm at it, apparently not. This is just a reminder from yesterday. It looks like it got scrambled a little bit, but yeah, so it looks like we've got our vector equation, and then our parametric form got all messed up. I don't know what happened there. And then, of course, down here would be the general equation for the plane. Okay, let's move on and get to the new material. Okay, so equation of planes using the normal vector. Okay, I think we can all agree. Let's take this pink vector AP, right? And this normal vector n, right? We should be able to agree at this point that if I took the dot product of those two, it should equal 0, right? If they're perpendicular, right, those two vectors should have a dot product of 0. So AP is a known point and an unknown point. The unknown point is P, so X, Y, Z. The known point is A1, A2, A3. So when we do this, we're going to be taking that vector, right, and we're going to be taking the dot product of that with n. And we want n, which we'll just call for the sake of this ABC, we want it to equal 0. So at this point, I don't have enough information here necessarily to come up with the equation here, because I've got 9 unknowns. Intentionally, the x, y, and z are unknown, but these values here are also unknown. We wouldn't be able to come up with what the equation of this plane would be quite yet. But on the next example, we will. Okay, so here we are. Find the equation of the plane. Given that these points, A, B, and C, are part of the plane. So first thing I'm going to want to do is I'm going to want to find vector AB. And using the points given, I'm not going to write it up there, not enough space. Vector AB will equal 2, 1, 0. Right, 4 minus 2, 3 minus 2, 2 minus 2. Vector AC would be negative 2 minus 2, 1 minus 2, 0 minus 2, which is negative 4, negative 1, negative 2. Okay. Now, how could we find a normal? How could we find something perpendicular to both of these vectors? Well, that, my young pupils, is called the cross product. So if I cross AB with AC, I will get the normal. Okay, so let's do that. Okay, crossing AB and AC. Here's the process, right? We set it up I and J and K. And so I'd have a 2, 1, 0. And I'd have a negative 4, negative 1, negative 2. So I'll come out with this, let's do it down here. I'll come out with this component-specific vector. So AB cross AC is going to be equal to the normal vector, which will be, okay, imagine now for a second, we find I, that means, or yeah, we covered up I, so it'll be 1 times negative 2, which is negative 2 minus 0. So I'll have negative 2I. Okay, now I cover up J, that's negative 4 minus 0, but remember it's minus that value. And then plus, cover up K, I get negative 2 minus a negative 4 is a positive 2K. So our normal vector in this case will be negative 2I plus 4J plus 2K. Alright, so we could also call this in this vertical form negative 2, 4, 2. Okay, now we're going to take that normal vector and we're going to take this vector AP, right, on the plane, vector AP. We know the points of A, right, those were given. We don't know the points of P. We'll call this X, Y, Z. But we do know A. A was, what was A? 2, 2, 2. That's easy enough. Okay, so vector AP would be all the points of P minus all the points of A. Well, that'd be X minus 2, Y minus 2, Z minus 2. And we're going to do the dot product with our normal vector. Our normal vector was negative 2, 4, 2. Now what we know about that is we want it to be equal to 0 because vector AP and vector, our normal vector, are perpendicular. Okay, so let's do a little dot product here. That would be negative 2 times X minus 2 plus 4 times Y minus 2. I think you see where this is going, plus 2 times Z minus 2. That's going to be equal to 0. So I'm going to distribute. I get negative 2x plus 4 plus 4y minus 8 plus 2z minus 4 is equal to 0. Let's combine some like terms. I see a 4 and a negative 4. Those will cancel. So it looks like I get a negative 8, which I'm going to bring over here as an 8. Okay, and then I think, well, that gets rid of that. Yep, so we got negative 2x plus 4y plus 2z equals 8. And that, folks, is the equation of the plane containing those 3 points. Let's do a quick highlight. I'll do a larger. There we go. Now I can highlight that quicker. That is the equation of the plane containing the points A, B, and C. The normal vector, you guys, is so useful. You'll see that throughout this lesson and the few to come. All right, let's do another example. Hang on, there is one more thing I wanted to add in here. Do you see anything fishy about the equation of this plane and this normal vector here? Each of the coefficients of x, y, and z are the same. That is not coincidental. We're going to see that on the next page. Okay, so I want to find the equation of a plane parallel to that vector through point 333. So the first thing I want to do is I want to find a normal vector. The nice little trick I showed you on the last page is that finding a normal vector given the equation of a plane is easy. It's going to be x plus 2y minus 3z. All right, you could also write that in this form, 1, 2, negative 3. It's always these coefficients, you guys. Always, always, always. The normal vector is the equation of the coefficients of x, y, and z. Now we want to find the position vector through point 333. So the position vector through point 333, well, we don't know where it's going. Okay, So what we would do is define that position vector AP, right, our friend. Remember, AP dot with our normal vector is equal to 0. So we know our normal vector, we just did it right here. We want to find AP. AP is always x minus x, y minus y, z minus z. So the 3's are the known z's, the x, y, and z are the unknown z's. Now what we're going to do at the end here for step number 3 is we're going to do the dot product. Take the product of 2 with 1 and then solve. So I'm just going to take my AP, this is my vector with a known point and unknown point, dot it with my normal vector, set it equal to 0, and we'll be able to find the equation of the plane that's parallel to the last plane we did, but doesn't go, like, goes through a different point, 3, 3, 3. Okay, so what we're going to see here, you guys, is something pretty cool, but let's do the work first. So that's x minus 3, y minus 3, z minus 3. And I had, what is that, 1, 2, negative 3. Okay, let's do the dot here. So that's x minus 3, I'm just going to distribute as I go, plus 2y minus 6, and that'll be minus 3z plus 9. Did I do that right? Plus 9, minus 6, minus 3. Okay, good. I'm going to combine some like terms here. Negative 3 and negative 6 and positive 9. They cancel. So I get x plus 2y minus 3z. Again, that was supposed to equal 0. So that will equal 0. And it looks like I can't get rid of that, but I wanted to get rid of this equal sign. That's the equation of our plane. Now the only difference between this equation and the one on the previous page is that the constant has changed, right? Nothing changed with the coefficients of x, y, and z, just the constant changed. So we saw on the previous page some value, I think it was, what was it? Was it 8? I think so. Yeah. No, actually, this is totally disconnected. Anyways, I've got this plane here, right? It's got a constant of 5, and now this plane is parallel to it, but obviously that constant has changed. Now all of the coefficients are the same, but the constant has changed. That means they're parallel, but not coincident. All right, two planes are parallel if, right, if the normal of the first and the normal of the second, this is not, just a reminder, this is not the cross product, but if they are scalar multiples of each other, right? So just like we did with parallel vectors, if the direction vector was a scalar multiple of the other, then they were parallel. In this case, same thing, right? And two planes are perpendicular if their normals are perpendicular. So are the set of planes parallel, perpendicular, or neither, given the following information? Okay, what we would have to do is, first of all, I can confirm it looks like the first normal vector is not equal to or not proportional to a scalar multiple of the second. So we know that they are not parallel. Okay, not parallel here, not parallel. Okay, but the second one I got to do a little work for. So I'm going to take the dot product of the first and the second and just see what happens, see if it equals 0. So n1 is 3 negative 1 square root of 10, dotted with n2, which is negative 3 1 root 10. It looks like I get negative 9 plus negative 1 plus 10, which equals 0. Therefore, we know that that the two vectors, whatever they are, or the two planes, whatever they are, I mean, I don't know their equations, but I know that their normals are perpendicular. Therefore, their planes are perpendicular. All right, this is a really good problem. I'm going to go ahead and work through it. This is kind of an extension, but you can choose to or not to work through this. It's just a really challenging problem that's actually pretty interesting. So, okay, so the first plane and the second plane are given, and they are perpendicular. If both planes contain the point 1, 3, negative 1, find A and B. Okay, so what that tells me is, first of all, this, right? That tells me that the normal vector for that plane would equal 4, negative 1, 6. And the normal vector for this one here would be A, B, negative 1. And so that'd be the normal for the second vector. Okay, now if I know that, I also know that if they are perpendicular, then the dot product of the two should equal 0. Therefore, if I execute a dot product, I get 4A minus B minus 6 should equal 0. Okay, now we're almost there, right? We're going to have to do some work because that's two variables. We're going to have to do a little bit of work. If I know that 1, 3, negative 1 is a point on both of those planes, then what I can do is plug 1, 3, negative 1 into both of them. So let's do it for the first. 4x minus y plus 6z equals negative 5. Okay. Actually, I don't need to do that. That should be true. Whoops. Let me try it for the one with the unknowns. Let's look at the other vector. Let's look at the blue one. Right. So ax plus by minus z should equal 7. So if I plug in 1, 3, negative 1, I'll get a plus 3b minus a negative 1 would be plus 1 equals 7. So that tells me a plus 3b equals 6. And so if I were to take this down here, I could rewrite as 4 minus b equals 6. And if I know that a plus 3b equals 6 and 4a minus b equals 6, then I know that a plus 3b has to be equal to 4a minus b. And then I can solve. I get 3a equals, what would that be? 2b. That's a terrible idea. Better idea coming. Ready? Whoops. Why don't I just do some elimination? A plus 3b equals 6. 4a minus b equals 6. How could I eliminate one? Let's eliminate b. Let's multiply by 3. Okay, so the first one would stay the same. The second one would become 12a. What is that? Minus 3b equals 18. I add those together. I get 13a. B's cancel. I get 24. So it looks like a equals 24 thirteenths. Now I could plug that back into any one of these other formulas. I'm going to plug it in here. Okay, so I'd get, oops, not there. Let's try again. How about here? That would work. 24 thirteenths plus 3b equals 6. Okay, so boy oh boy, 6 thirteenths is 60, 78. So that would be 78 thirteenths. Okay, let's do that. So then when I subtract, I get 3b equals, that'd be 54 thirteenths. So when I divide by 3, It looks like I get 18/13. So there you go, folks. It looks like using a process of elimination as well as just a general knowledge of vectors and their equations of planes and normals, I can come up with those values for A and B.